recording. Go ahead, please.
I hope everybody can see the
I don't think your microphone is on.
the application in a moment where we have derived a class, your detector construction. We have mapped override the structure and the construct method that we have still to implement. And we have implemented some setters and getters for some properties of all that. But I have drawn here in the blackboard is the geometry that we will implement in a moment. The world volume will be a box that and inside. Sorry, thank you for noticing. Sorry, as I was saying, we left intermediate application still pending. Was the implementation of the construct method. In this method, we will implement the materials and geometry of our experimental setup. Here in the blackboard, I have drawn what we will implement for the world volume. That is a typical name that you will see in every Jam4 application. Is the most top volume in the geometry hierarchy. Will be a box, and inside we will place our target to record the information during the simulation. If you remember from the slides, we have to provide to the constructor of the box half size of the dimensions. In our case, we have implemented as private member of our detector constructor the thickness. So this part here represents half of the thickness of our detector constructor. We will align it along the x-axis, and on the perpendicular axis, we will put different dimensions that will scale with this thickness. And of course, because the target volume will be placed inside the wall must be bigger. So we will apply other scaling factors just to define our wall. This is just a very simplified manner to define our geometry. As I was saying before, geometry can be extremely complex for real detectors, and but we will not go into that direction. If you want to know more details about the geometry implementation and all the features that Jam4 provides, please take the advanced course. There are several sessions about the geometry details. So now we can go back to the code and implement the construct method that will define our geometry. Okay, shall we stop sharing the camera, or it's okay if I start sharing? Okay. 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 Why there is this? I don't understand. Sorry. Okay. Okay, so we leave it here. Now we can continue with the implementation of our class. To do so, we have to create a new file. We can use it. We can create a new file also from Gedit. If we click in this plus on the top left corner, we can save it by clicking in save. And we have to save it in local one work intermediate application. This will be the implementation of this class, your detector construction. So the name of this file should be your detector construction.cc. The first thing we have to do in this file is to include the header of the class, your detector. The link to Mattermost. Gabriele, can you share the link to the Mattermost day 2, please? So we will include the header, and now we have to implement the methods that we didn't implement here. Basically, almost all of them. We can start by the constructor. So the constructor.
Uppercase.
Good point. Thank you.
And this goes into source.
Yes, this file is placed. Maybe you cannot see it because it's terribly small on the top. This is placed in the source directory. We can go back to the terminal, go one level up. So we are in intermediate application directory. We have the build directory, the CMake list, include our application.cc with the main function, and the directory are src. If we check what is inside, now there is a file called your detector construction that we have just created using Gedit directly.
And it's part of the CMake, whatever configuration that it will look inside of source.
This is a very good question. So the question is how CMake knows about this new file. So we can take a look to the CMake list by typing Gedit CMake list if you want. Otherwise, you can simply see my screen. If you remember at the beginning, we were not paying too much attention to these lines. But basically, these lines, what are telling to CMake is that these lines are defining a list of files called sources, and this list of files will correspond to all files that are in this directory source, and with this extension. And also it will create another list of header files called headers, and with all the files in the include directory. And when creating the executable, these lists of sources and header files will be passed at the compilation time. This line was simply ignored before because the directory was empty and the list was empty. And thank you for the spelling mistake. So this will be our constructor. The first thing we have to do is initialize some components. The first thing we have to initialize is the base class constructor. So we can simply go back here and copy paste the name, because otherwise the probability of writing it right the first time is very low. So we can copy and paste it here. And by doing so, what we are doing is initializing at the same time the constructor of our class and also the constructor of the base class. This is important because sometimes some base classes may initialize some internal components. So we have to call this. Good. Now in the constructor, what we are going to call is the setters. So we are going to set the target material to be G4 silicon. And we are going to set the target thickness to be 1.0. Do you think this is correct as it is now? Very good. So we have to include the units. We are going to say target thickness, not 1, but 1 centimeter. Now, similarly, we have to define a destructor. In our case, we are not storing inside this. We are not storing inside this class any object or shared resource. Therefore, our destructor can be as simple as this. If you are creating something, you have also to delete it when the application ends, when the object is being destroyed. Now we can implement the setters. Because if you remember, we implemented the getters here, which were naive. They were just returning the value or the pointer, but we didn't implement the setters. So now we can implement them. Okay. We can start by implementing the target material. So your detector construction set target material. Key for string mat name close. So if you remember from the example, we will retrieve directly from the NIST manager the material. So we can do something like G for in one single line, G for material asterisk mat equal G for NIST manager instance. This will create or retrieve the instance of the NIST material database, and then find or build material. And we pass as argument the map name. Now, do you remember from before what happens if we ask the NIST manager for the Philosopher's Stone? That we have a null pointer. So what do we have to do here? To cross-check if the return value is null or not. So we have to cross-check if null pointer equal in this case mat. You have this is another good practice. Const values or const expressions should always be placed on the left on a logical operation. This is done to prevent stupid errors. For example, if instead of equal you put equal, this will be compilation error. However, if you do the other way around, if you do like this, but then you forgot to put one equal, this is not an error. This is true or false. In this case, it will be false because you are assigning a mat a null point. So, as a good practice, put const values. In this case, it's a null pointer, but if you are checking for a value, please put the literals or the const values always on the left. So null pointer equal mat, and then we do something similarly to what we did for the Philosopher's Stone example. We will trigger an error with G for share, common error output, and we will say error in, again, good practice to say who is triggering the error, because otherwise you will simply say that something went wrong. So we will copy paste the name of the function. So error in your detector construction set target material dot. We can continue in the following line. This is acceptable. Material mat name not included in jam for NIST manager. And then G for end of line. And then something that I personally like, and this is a behavior that you will see, is that if a C++ program has to fail, it should fail as early as possible. Otherwise, it may be running with a wrong configuration, or it may fail silently later. So in order to abort the execution of a program, we can use the C++ function exit with a code -1. In case we if we try to set up a material that does not exist in Jam4, instead of assigning a material that is a null pointer, it will simply make the application explode. It will exit.
Where did we import the material, what is it, the constants, CLHEP or G4 Nest Manager at this stage? Is this also just implied somewhere? Or?
The question was, where does this source code or the compiler find G4 material and the CLHEP units?
That is a very good question. As it is now, we have not done it. So we can add now the include if you want. G4, which includes shall we use? Just the G4 NIST material, NIST manager, or also the G4 material, or both?
The material has been forward declared earlier.
Yes, so we should include G4 material because we promised the compiler we will declare the class. And because we are using the G4 NIST manager, we have also to include it. It doesn't matter if if the G4 NIST manager is also including the G4 material, because as we saw earlier, all the classes in Jam4 will be protected with this preprocessor word macro. So if whatever variable is not defined, they will define it. So this will not be an error if we include twice the same header or if G4 material is already included in this manager. Okay, thank you. There was a spelling mistake. Oh, yes, thank you very much. Thank you.
Give some insight why it's better to import it in the source file and not in the header file.
Yes, we will see later a practical case where it is better to do forward declaration, but basically you should not do include of classes that you are not actually using in the header. And in theory, in the header, you should not be using any class because it's just a declaration. You will be declaring the methods, you will be declaring some members, which might be pointers. Of course, if you are passing by copy, for example, G4 string, and G4 string was not included before, you will have to, because you are actually using it. The compiler must know what are the classes being used at each step. But for example, G4 material in the header, as it is, we are not using it. We are simply saying there will be a pointer to a G4 material. But the compiler does not need to know more about G4 material. However, now we need to include G4 material because we are going to deal with materials. Maybe not much now, but later in the construct when implementing the construct method. Okay, the next thing we have to check is if the material is different. So if material is different from F target material, then F target material equal mat. And as we were saying before, if we are changing the target material, and this is the line 24 that we just written, we have to notify the run manager using this syntax. And again, because we are now using G4 run manager, we need also to include a corresponding header. So on the top, we have to write hash include a space between quotes G4 run manager.hh. Every time we change the material of our detector, we should notify the run manager. If the run manager has not been initialized, this will have no effect. This may have effect once the simulation has been running, and we do this after a run or after initializing. Okay. Any questions so far? Everybody has been following? Please, yeah. Yes, this is the first time we are calling it. We should create a run manager in the main application later tomorrow. At the moment, we are simply calling it. Again, with this method, run manager.get run manager, Jan4 will know how to retrieve the proper run manager and notify that the physics has been modified. We will create it tomorrow. Thank you. The question was why, if this was the first time we are calling the run manager. Yes, so far it's the first time. Okay, so we can now implement the other setter. So we can type, I will some spaces here. Your detector construction set target thickness G4 double thickness and we would do something like this: F target thickness equal thickness. And we have also to notify the G4 run manager that the geometry has to be reinitialized. So we have to say reinitialize geometry. By doing this, it will call the construct method again. Do you think the code it's okay as it is, or
Do you check if thickness is 0 or infinity or
good?
-1?
Yes, at least let's try to add an if statement to make our code more robust. This is in general something that you should do. So in our case, again, constants on the left, if thickness less or equal to 0, we can put a G4 error. Again, we have to notify from which function we are calling. Error in your detector construction dot set detector thickness. We can continue in the following line. Thickness must be positive.
And here again, you put the constant or the literal on the left.
Yes, the constants should always be placed on the left. This is just, it will not make your code run faster, but in case there is a mistake, for example, if you try to do something like this, this will be a compilation error. And we can return earlier without doing anything else. We can also do an exit. We can return as you wish. The important thing is that you print out what happened. Please don't program code that do things silently or assuming things. It's better to be verbose if possible. Then the verbosity can be tuned, but it's better to offer some verbosity.
Why do you return here? And earlier you exit.
Return will simply keep the program running without making the program exit. If we exit, the program will end immediately. It's a matter of taste if you want your application to explode or simply handle things more gracefully. Okay, and now that we have all the functions, methods, the only one that remains is the big one, the construct. This one will implement the geometry of our experimental setup. So we can copy the definition, the declaration from the header, and we can go here. It will be it belongs to your detector construction. So this method will return a G4V physical volume asterisk pointer, and every method should be defined within the class. So we have to put the name of the class dot construct, okay, like this. And now, as a full recap of all what we have seen, we will need to define two materials, one for the world volume, one for the target volume, the two boxes that we had in the blackboard. And then we will build the geometry. So we can start by the materials. We can put a comment with double slash. So the first step is to create materials. We type G4 material asterisk world material name. We will use a material called G4. Sorry, with lowercase. Okay. The other G4 material is actually the variable f target material that we have already initialized in the constructor by calling the method set target material. Because in the constructor we set target material to G4 silicon, this function, this method is already setting up this. Yeah, sorry?
You define the physical volume directly. Do you need to define a logical volume before the physical volume and then include it?
We will include the corresponding headers as we will need it. At the moment, we are just dealing with material, so we have included the needs manager and the G4 material headers. We will include in a moment this G4 solid, the G4 box, which is the solid that we will be using, the G4 logical volume, and the place volumes.
Okay.
Thank you.
Thank you.
Yeah, the headers can be added as we need them.
Excuse me.
Yes.
Isn't it better that after every section we make and check our code is running, or you want to complete and then you make it?
We can try now, or we can try at the end. That is a bit the taste of each one. If you feel maybe more insecure, you can write a piece of code, go compile and check it. Ideally, what one should do is at the same time you are writing code, you should be writing tests, unit tests to the code that you are writing. So the test should not be only the compilation, but there should be also another piece of code that will review that your original piece of code is doing what you expect. And however, due to limitations of time, we cannot implement this kind of method. But yes, there is a full way of coding called test-driven development. And basically, it means that first you write a test that originally will fail because you will have no code, and then you will have to implement the code based on the tests. So first you implement a test that will test some feature that does not exist, then you will implement the feature, then the test will pass. And then you will improve the test or add new tests, and then you can keep developing the features as it is. This will make your project very robust. Thank you. Okay, so we have at this point, sorry. The world material name is actually not a pointer to a G4 material, it's a G4 string. And we have to retrieve the G4 material, world material, from the NIST. So again, G4 NIST manager dot instance find or build material. Sorry, because I have not much space. I have to break the line. Find or build material, word material name. Usually it's a good practice to initialize variables first and then use them, for example, in the following line. It is possible to, instead of passing the world material name variable to the NIST manager, we can also hard code it here. G for, please don't do this. You can also do that, but it's usually a bad practice. We were doing it yesterday just for educational purposes because we wanted to go fast for the G4 element isotope definition, but you should not do that. And what is more, for values that are actually not changing during the program or even during the entire application, we can mark them with const. You should mark with the const keyword every variable that should not change and every method that should not change the content. For example, we could mark as const the getters like this. This will not change the logic. This will only trigger a compilation error in case these methods are used. In case these methods try to change the internal state of the class. And this is also a promise for anyone using this method. So most of the time you will see that you are using a function or a method. And if it is marked as const, this is a promise that a very hard promise that it is not changing the internal state. So it is already giving you some information about how it works. You can, you should use const wherever it is possible. Okay, so at this point, we will have already the world material. So now we can start creating the solids. Now, for defining a solid, for a box, for the target, so we can say target solid. If you remember, the arguments were the name. I recommend you to give always verbose names so you will remember. And now, let me check. Yeah. We have to pass half the size on each direction. So we will use variables that still do not exist. We will define them in a moment. Okay, this is how we would define a Jam4 box. Now, if you remember from the Blackboard, the target size will be G4 double, and this will correspond to the F target thickness. Now, for the other size, we don't care much. So we will take as reference the target thickness and we will scale it. So we can define an intermediate. Okay, let's do first bad and then we will show you how to do better. We can define a double target Y size, which can be 1.25 times F target thickness. And we can define the target set size equal 1.25 F target thickness. Okay, this is bad. You should never put magical numbers in a code. This is not, for anyone reading the code later, this is not meaningful. There are different levels of doing things good or bad. So we can try to make it better. How? We can define a G4 double that would be target scale factor, and we can call it like this, and it can replace the number. Does the code tells you a bit more information than before? You have to choose wisely the variable names, so the code can be understood even without knowing much. You have to be able to transmit the ideas that you had in mind when writing the code for anyone reading the code later. Okay. We can also define the box for the world. Okay, and as before, we can define a world to target scale factor, which can be 1.1. Now we are going to define all these world size XYZ as world to target scale factor multiplied by target X size. The world should be bigger than the target because the target volume will be placed inside the world. So that is the reason we use a world to target scale factor of 1.1. It means that the world will be 1.1 times bigger in every direction with respect to the target volume. The target volume will be a box that will be or sensitive volume, if you want, or volume of interest, and the world volume will be bigger. It would be like the room or the main. It can be whatever you decide is the most top volume in your setup, and will be always bigger. Yes. If the world volume is smaller than the target, what will happen is that you will be creating something called overlap. And it means that the geometry is not good for navigation because the daughter volume is protruding the mother volume. It would be like a glitch if you want. It's like when you are playing video games and then suddenly you see that you can half cross the wall. That is bad. The daughter volumes should never get out of the mother volumes. If do so, they will create a problem during navigation. And Jan4 offers ways to inspect that. You can get more information in the advanced course or in the documentation. Unfortunately, that goes beyond the scope of this course.
So if there is overlap, the code will run or?
Yes, it will run. And if you are lucky, so the question was, what happens if there are overlaps? For example, the daughter volume getting out of the mother volume, for example, by defining a too small world volume in this case. So if you are lucky, you will have a warning printed out. If not, you may have a problem during the navigation and you will not notice. And this can cause, of course, it may have consequences when recording information out of the simulation. To ensure that the navigation is correct, the detector volumes should not overlap each other, and they should not be placed outside the mother volume, wherever they are placed. At the moment, the target thickness is it's set up in the constructor, and in case you modify the target thickness after the construct method is called, the run manager will be notified, and the run manager will call again the construct method with the new thickness that you specify. So the set target thickness is not only setting the new target thickness, but also asking the run manager to reinitialize the geometry whenever it is possible. At the moment, we didn't. So the question was if we can change the scale factors. So actually, we didn't put any setter or getter to these scale factors. These factors are hard-coded. We will see later, if we have time, how to improve the situation. But at the moment, the values are hard-coded as it is. This is not the best practice, but this is the best we can do at the moment. This is just a way to scale the whole geometry based on the target thickness. In realistic detectors, you will not have this situation. Okay. So now we have the solids. So now we can create the second layer, the second conceptual layer of the geometry, which are the logical volumes. So we can create logical volumes for these solids. If you remember, the logical volume is just the association of a solid with a material. The materials were defined here. We have the world material, and that we retrieve from the NIST manager, and we have the target material that was set up before. We have just defined the boxes, the target solid and the world solid before. So now we can create the logical volumes for these ones. To do so, we do G4 logical volume target. You can write down all logical volume. You can simply type LV as you wish. Yes, thank you. There was a mistake from my side. So G4 logical volume should be target LV should be a pointer to a logical volume, not an object by itself. We are assigning it with new G4 logical volume. And if you remember the mandatory arguments. Sorry? No. Okay. So we have to provide the name, target logical volume, for example, target logical. And now we have to provide material and the solid. Sorry, and I changed the order actually.
Of course, it was a rhetorical question in this case.
Actually, I should. So how to, if you don't remember the arguments to create a logical volume, for example, imagine that I don't have the solution, the code that is coming from the final application. What we have to do is open, for example, with gedit, we will go to the installation directory. So you don't have to do this. I will show you only what you will need to do because it's tedious, takes a bit of time. You can also use GitHub, which is much faster. So we can go to include, to Jan4, include Jan4, and now we can look for the header G4 logic. Sorry, it's a glitch of the virtual machine. I have to close the gedit. Okay. So if you don't know what are the arguments, you can go always to the header file of the G4 logical volume. Look for it here, G4. So G4 logical volume. Okay. So this is the class G4 logical volume. Here you have the explanation for the arguments, and here you have the arguments that are mandatory, that do not have a predefined value. So the first argument actually is not the name, is the pointer to the solid, in our case, the box. The second argument is the material, and the third one is the name. So now we can go to our detector constructor.cc. Actually, this is not correct. The first argument should be the solid. The next argument should be the target material, and the third one should be the name. Okay. Is everyone still in sync? Okay, we can create a logical volume for the world. We can call it world LV, new G4 logical volume, and it will follow the same structure as before. So we say the first argument to the constructor is the world solid. We will associate it with the world material, and we will give it a name which has to be meaningful. For example, world logical. Okay, so this was the second conceptual layer of the geometry in Jam4. The logical volume is just the association of a G4 material and G4 solid. At this point, we can also add other features to the logical volume. We could attach, not in this function, but later in somewhere else, a field, a sensitive detector, some user actions, doesn't matter. At the moment, we are going to keep it simple. And finally, we create the physical volumes. The physical volume is the association of a logical volume plus a 3D transformation, a placement in our geometry. Okay. And again, what are the arguments of the placement? Impossible to remember. So we are going to use among the different options that Jam4 offers. If you remember, there is the possibility of placing, exploiting the symmetry of our setup and using some replica or division to place the same volume many times, or to divide a volume into parts. We are going to use a simple placement. To do so, we are going to use the class G4 PV placement. We can access to it in user local Jam4, and we can look for it. G4 PV placement. Here it is. And again, we can go to the constructor, and you can see here the arguments that we may have to provide. So we may provide a rotation matrix in case we want to place the object rotated. In our case, we don't use it, so we will pass a null pointer, the translation, the logical volume that we want to place, the volume of the placement, and the pointer to the logical volume of the mother. Okay. So we can go here to the bottom, and So we can write G4B physical volume. This is the base class. Even if we are using a derived class, which is a placement, it doesn't matter. As we saw with during the warm-up part yesterday, we were passing as arguments cubes and a sphere to a function that was printing the volume and was taking as argument any solid. Similarly, here we can use the pointer to the base class, but even assigning it to derived classes as a placement. So, for example, we can say, sorry?
G4P.
Physical volume. No, sorry, a typo where?
G4PV placement.
No, but this is not the placement. This is the base class. So the base class of a physical volume is G4B physical volume. And then there are different derived classes. One is the placement, that is the one that we will use. And there are others such as replica and division or parametrization that we will not use. But we can still use a pointer to the base class because all those, the placement and others, are derived class of this one. Yeah. So we can say target physical equal new G4 PV placement. So now if you remember the arguments, the first one was the rotation that we will not use. The second one is the translation, which is just a vector. We will see. Here, G4 3 vector. So we can write here, hopefully, G4 3 vector. Okay, but we don't want to displace to put any offset to the target volume. The target volume will be placed exactly at the center of the world. If you want to create some offset, you can modify this value. The next argument that we have to pass is the logical volume that we want to place. So target logical volume, and we have to say in which at the name and in which logical volume, what is the model in which we will place it. In this case, we will call it target physical, for example. And the target will be placed into the world. Okay.
My understanding was still lacking P many and P copy number parameters.
Yes.
Some parameters have default values you don't need to worry about.
But in this case, we have to do are not, no?
But how do I know if it's a default?
In this case, you can see that, for example, psurf check has a predefined value. The others are not. If you try to skip it, you will have a compilation error.
What I can assure you is whatever value you give to many, Jean4 will ignore it forever. Copy number is useful though. Legacy issue.
Yes, if you read the documentation that is just on top, you say P many flag to identify if the volume is meant to be considered an overlapping structure or not. Space, not use. So please read the documentation carefully if you want to really understand what you are dealing with.
And sorry about the legacy issue, but 30 years ago, a decision was made to leave this in the interface as it existed in the previous version, Jean3. And then we made the design decision not to implement what had been implemented in the past this way.
Okay. We can do something similar for the world. So we can say G4B physical volume asterisk world physical equal new G4 PV placement. And because this is the world, we will not rotate it. We will not move it anywhere. So the volume will be, adiós. Joder, estamos dados. Sorry, I have to exit. I think I stopped sharing. Sorry, I have some technical difficulties here. Can you pause the recording, please? Thank you. Okay, thank you. Sorry for the technical difficulties. So we were placing the world as a final step. Thank you. So the first argument is the rotation matrix that in our case, we will not use. The second argument is the translation vector that we will not use. The third argument is the logical volume of the world, which is in our case called world underscore LV. The fourth argument is the name of the placement, in our case, world physical, for example. The fifth argument is the mother volume. And because this is the toppest, there is no other mother on top. So we will put null pointer. And the other two arguments, as we did before, false and 0, because we will not use copy number, and the other one is. Now, we have written all this code, but if you remember, this construct method should return a pointer to the world, actually to the physical volume that points to the world. So actually, we have to do a few things here before finalizing the function. We have to return physical, the physical placement of the world. And if you remember, we define a third internal member. One, we defined as internal members the target thickness, the target material, and the physical volume of the target. So we have to, let's check first what was the name, because honestly, I don't remember myself. So if we go to the class implementation of your detector construction, you see that we have a pointer F target material that points to the material of the target, a G4 double F target thickness that stores the target thickness, and a pointer to G4 physical volume of target that will point to the target physical volume. So we could here write F target physical volume equal target physical, for example. So the placement of the target, the physical volume that contains the placement of the target, it's an object, and the pointer will be stored in this variable internal to the class, F target physical volume. Now, do you miss something? That we have been writing a lot of code. Do you miss something at this point? The last two, these ones. So yes, this is a good question. The question was, why do we need to store a pointer to the placement of the target volume? This is a piece of information that we will need later when we want to store information of what is going on during the simulation in this volume. During the simulation, we can always know, are we in this place volume or not? So in order to do so, we can check it like this. Okay, so we have been missing few things, mainly the headers. So these are the headers to construct materials. The run manager is general purpose, is just to notify. And for the geometry, we need to include some headers. So we have to include what are the classes that we have been using. G4 box. We have been using G4 logical volume. A logical volume is a composition of material and the shape, in this case a box. We have been using G4 PV placement. Do you miss something else? So we need to include, yes, the solid shape that we have been using, G4 box. If you use other shapes, you need to include the headers corresponding to those. If you use a sphere, you need to include the G4 orb or G4 sphere as you need. The logical volume is something that you will need to load always, and the placement, well, if you are placing one by one, you need to call it also. Okay, everyone is in sync with this? Let's compile. Back to the terminal. Do you think it will compile? Of course not. That is the attitude. So we go back to the terminal. We change directory to build. And we type make. Sorry? Very good. You notice that our class was not being compiled. Okay, so we need to tell CMake to update, to watch out, because now we have included a new file. So CMake created in this build directory something called CMake cache.txt and some other files. Those files are containing an information to compile the project. But if in the meantime we have changed that, we may need to tell CMake, watch out, there are new files. To do so, we can simply say from the build directory, CMake ... This will reconfigure the project and in a different manner. And now we can do make again. And now there are some errors, of course. Okay, first difference with respect to before, as our colleague already noticed, is that now we are compiling your detector construction.cc. Very good. If you change your project, you have to tell CMake that you change it. Now we have to interpret what are these errors. So the compiler is telling us your detector construction.cc at line 48, character 42. Yes? Sorry? 78, sorry. Expected primary expression before the parentheses. And here, at least the compiler sometimes is kind, and the compiler will tell you, maybe you wanna, this is a spelling error, and maybe you wanna use something else. So in this case, it's already telling you, you wrote world underscore material, maybe you wanna say world material without the underscore. So the compilers nowadays are very smart in this sense, and very kind. So we will inspect first this error in line 78. We can go here, line 78. The error is this. I placed a comma after the last argument. This should not be there. Okay, we save. The other error was this world underscore material does not exist. The name I gave at the beginning was world material. Very good. So now we can go back to the terminal after correcting these errors. Do make, and it compiles. But so far, if you remember, we didn't have much in our main. So if we go back from the build direct, if you're still in the build directory, you can type gedit space ... or application.cc, because if you remember, it's empty. Basically, what is happening now is the code is being compiled, the header is being included into the main function, but it's not being used. However, we can create an object of type your detector constructor, and now the code will be executed. Some code will be executed, at least the constructor will be executed. Do you think it will compile or not? Okay, I will leave it up here, so you can still see it. So now in the main function, we are not only including your detector constructor.hh, but now we are creating an object, your detector construction space asterisk space detector, that will be the name of our variable, equal to new your detector construction, open close parenthesis, semicolon. This will create a detector, and this will call the constructor of the class. We can go back to the terminal, do make. Sorry? So we are in the, yeah, this is a good question. In the main function, in the main file or application.cc, we should only include the header, your application construction, your detector construction.hh. Then in the CMake, we can take a look to the CMake again. So gedit space ... slash CMake list.txt. If we take a look to the CMake again, we see that CMake this was copy pasted from the example basic v1 provided by Jan4. CMake is creating a list with called sources with all the files in the source directory. Then when it's creating the executable by doing add executable or application, this is the name of our executable, we are telling CMake use the file or application.cc and all the files in the list sources. there is where CMake will understand, the executable is actually made of several CC files, the main one, and all the files inside the source. And it's now responsibility of CMake and later the compiler to compile the code and put everything all together. Yes, and the include has to, it's a bit more tricky because actually it has to be provided in several places. So it has to be provided in as target include directory, private include, and also in the list of files to be added in during the creation of the executable. Yes, this is just to tell CMake where to find the different files, and the executable is made as all the CC files. If you remember from yesterday, we were doing at the very beginning G++ a file or application.cc, but you can put as many CC files as you want, and then everything will be compiled all together. Good. We will
show me our application. It's also there.
Sure. So our application contains the include to our class, and then we create a pointer to this new class. Okay. Okay. So now we can try to run, and we have a segmentation fault. Do you guess why? In which point we might be dealing with a null pointer, which is one of the causes of a segmentation fault. So if we go back to your detector constructor, we see that our code is actually relatively naive. We are even checking if the material exists in the NIST manager. And then if the material exists even, we are assigning to target material. So we are cross-checking for material node pointer, but then we are using this run manager, get run manager. But we are not checking if the run manager exists or if anyone created it. It doesn't matter. At this point, is good enough that the code compiles. We will create the run manager tomorrow. But we are using, as it is the code now, we are not protecting against the non-existence of the run manager. So that is the reason the code compiles, but if you try to run it, it will try to access the run manager and it does not exist. Good. Any questions so far? From remote? Yes, we can try to compile and without it. So what happens if we comment it?
Either people are following perfectly or they're too stunned to pose a question.
Yes, we can try to comment it and we will see that the error disappears. You don't have to do it. It's just for the sake of curiosity. Now the application runs silently, but it runs.
But for the sake of curiosity, you could also run it in the debugger and see where it crashes.
This is maybe a bit too advanced for this course.
Sorry.
Okay, so if
second, there's a question.
Pardon.
If we have to call the run manager to tell it that the physics has been modified, why does it run when we comment it?
Because when we comment it, so when we do this, let me check. Let me open it again.
So commented out the code that talked to the run manager.
So if you comment it, the code is like it disappears. It's like this never existed.
When the application will run, to run correctly, it requires this. But while you're testing it, you say, okay, I have not finished it. I will test the part that I've created. The run manager is not yet there. So
this is just for the sake of checking that everything compiles and runs without segmentation fault, or at least we understand the segmentation fault. Okay. Has anyone reached this point? Like you managed to compile your detector construction.cc and you managed to get to the segmentation fault?
Yeah.
Good.
The physics has been modified.
Okay. Perfect. Good. Very good. I will check also in the Zoom, but I don't see.
The main was also in the source.
Pardon?
The main function was also in the source. Or...
Yes. Sorry. I stopped sharing too fast. Yes. If you check the CMake list, the line 23, I believe it is, you have a function that is called add executable. So the question was if the main file or application.cc was added to the list of files to be compiled. So if you go to the line 23, I believe in the CMake list, there is a function called add executable, and then we give a name to this executable, and the first file that we provide in the list is actually our application.cc, which contains the main function. John, or Gabriele, do you think it's a good moment to make a 5-minute break? Yeah. Just for the people maybe to have a short break, or you think we can continue? Also to catch up. Because if John is busy back in there. Okay, yeah, let's make a 5-minute break. We should reconvene in 5 minutes.